So we're on page 3. We need to finish. We'll see if we have, I hope we have time to finish. I know, I always get, like I think we have plenty of time and then I look at the
Hashtag
clock.
story of my life.
We have like 45 minutes. I feel like that's a lot.
We're fine.
It was.
You know?
High time.
Okay, here's a whole bunch of words.
I miss you.
Oh, yeah, I like words.
I was.
The
We do
big
words
font
instead
is
of
like blowing my mind right now.
So the big font.
The bigger the font, the more likely you're gonna get it.
Oh, so some of you were asking, how do you know? Yesterday we looked at this graph and we looked at what makes it a local maximum or local minimum. You'll see this word nearby. It just means like if you can take, here's your big interval, the whole domain. If you can kind of zero in on one like a smaller interval and see that you have a maximum within that smaller interval, then that's a local maximum. Same thing, local minimum. Does that make sense? Like kind of like zeroing in on a smaller part of the graph instead of looking at the big picture. Okay, so just local extreme values or relative extrema. I don't know what you referred to it last year. Did you call it local? Or
In local, it was local. It was
Local.
local. I remember Mr. Duval's accent saying local. It was fun.
local. So just be aware on the AP exam they may refer to it as local or relative. So that's why you just need to know both terms. So local or relative. So local maximum at C, if all the values that are around it are going to be smaller than, or the local minimum if f of C is bigger than all the values.
IFF is if and only if, right?
If, yeah, the two F, if and only if.
Got it.
Why do you spell if with two F's?
She's telling you right now, I'm not.
So math people like to abbreviate because we don't want to write if and only if, it's just too much, so they just write IFF. If and only if means that if you read it one direction, it's true in reverse. So like I talk about this in geometry, like if two angles are congruent, then they have the same measure. If two angles have the same measure, then they're congruent. So we could just say two angles congruent if and only if they have the same measure. So it just means that both ways that I say it, the conditional and the converse, are both true.
Oh, really?
So
Logically, that doesn't really make sense. Oh.
yeah, but okay, so I could give you a different example. Like, I know it's been a while, but if I said right angles are congruent, you can't say that. Like, so if I have two angles that are right angles, then they're congruent. That's true. But if I say the converse, if you have two congruent angles, then they're right angles, that's not true. So you couldn't use the IFF for a statement like that. You can only use IFF if you could say it both directions.
I looked up IFF to see if it was an actual word, and it is in the military. It means identification, friend or foe. And it also then says mathematics, if and only if.
Thank you.
Did you think I was making it up?
No, I just wanted to see if it was also a word.
It is an actual word. Okay, there you go.
Then why spell check trans?
It does. No, it doesn't.
No, there are a number of words that we come across in math.
On my phone, it doesn't.
Anti-differentiation is another one that will.
Dr. Todd was upset about historiography.
I get upset when there's a lot of math terms that they underline and they say they're not correct, and they are. They just don't, word doesn't recognize it.
Science chem terms too.
Okay, finding.
What? When I was writing up the.
Okay, so we need to get through this. Finding extreme values. So one of the things, I want you to look, I'll scroll back to this previous picture. If we look back to this previous picture, let's look at the interior points. There's places where I know I have a maximum or a minimum value. So if we think of this in terms of the tangent, you'll notice here there's a horizontal tangent. What's the derivative when we have a horizontal tangent? 0. So here, here is a horizontal tangent. What about here? Not a horizontal tangent. Basically, this would be a corner. So this is where we don't have a derivative. The derivative does not exist. So all of these qualify as maximum or minimum points. So this is really important here where we have local extreme values. Or finding extreme values is where f prime is 0 or f prime does not exist. Now, we want to make sure when we're looking at this, we're actually looking at both cases because we don't want to forget if there's like a corner or a cusp. Those could qualify as maximum or minimum points. Okay, critical, this is just saying the same thing. Critical points are when f prime is equal to 0 or it does not exist. And it's something that's in the domain. So basically critical points are x values if they're in the domain.
And extreme values are y values.
Correct. So when I ask you to find the local maximum or local minimum values or our extreme values, those are y values. Where they occur are the critical points or the x values. Natalie?
This is f of c versus like f of s.
C is a point within the domain.
And what is f of s at any point in the domain?
Yeah, f of x would be referring to the entire graph itself.
Okay.
F of x refers to all the y values. F of c is a particular y value. Does that make sense? So when I say f of x, I'm referring to the whole graph, whereas f of c is a particular point. Okay, so in summary, yes, the big bold letters, extreme values occur only at critical points and endpoints. So those are the two things. Remember back here, we had this. So maximum and minimums are going to occur where we have critical points. 1, 2, we have 3 critical points here. These were where the derivative was 0. This is where the derivative is undefined. And then we also have at endpoints. So those are the only places where you could have maximum minimums. Shelby?
And it's only going to be like critical points and kind of weird graphs. Like for example, in example 3, you wouldn't have to check for a critical point because you know it's like just a straight line.
Right. You don't have to check for it. You only have to check at those particular places. Is that?
At the endpoints because like you already know what the graph is, but if there's some kind of like weird equation, you would want to check like every value.
Yeah. I think it depends. I mean, you'll kind of get used to when you have to check and when you don't. The first one is a parabola. So hopefully, I mean, some of them are going to be pretty obvious, but I still want you to show, you'll see this word analytic. Whenever I say analytic, that means use calculus. Don't just
Wait,
put it in.
calculator.
Not calculator.
Same thing, right?
No. Analytical, when I use analytical, it just means kind of make sure you show your work.
So we just said this will equal to 0 from my level or
Yeah, so here's what we want to do. Extreme values. So we're going to do the derivative. Okay, so do the derivative first. So that's going to be negative 2x plus 4. So to find the critical points,
There's nowhere where it doesn't exist.
right, so we're going to look at where is f prime equal to 0 and where f prime of x is undefined.
We do that.
It's not undefined.
Okay, so negative 2x plus 4 is not undefined. There's no, what we think of undefined when we have a rational function and it might make the denominator 0. We don't have that situation here. So we're just going to set negative 2x plus 4 equal to 0. So we get 2x equals 4, so x equals 2. That's our critical point.
If it was 4, then we would what if it was like 4
I don't want to circle that, sorry. I just wanted to, what's that?
What is the difference isn't it outside of the domain?
Oh, that's a good question. The domain, well, this
Oh,
domain
zero.
was given to us, we only wanna look at from 0 to 3.
If it was 4, then 2.
If you get a critical value, a critical point that's outside the domain, we're not gonna check it.
The other thing.
We just ignore it. So what we wanna do is we're gonna plug the critical point and endpoints back into the original equation. Okay, so I want to check f of 2, f of 0, and f of 3. Since I'm just looking for extreme, extreme just means absolute. I'm just going to look for the biggest one and the smallest one.
Wait, why are we doing it from 0 and
Oh, those are the endpoints. Sorry. 0 and 3. Those are the endpoints. Okay, so plugging in 2, you get what? Negative 2 squared plus 4 times 2 minus 5. We get what? Negative 1? And what happens when we plug in f of 0? We get negative 5, and what if, is it negative 1? Negative 4 plus 8. 4
What
times
is it, negative or 4?
Oh, because it's
Negative on the
it's
outside?
x squared, and then we want the negative.
Oh.
So it's not negative 2 squared, it's a negative 2 squared. It's like how you, it depends on how you see it. All right, what about f of 3? So then that's the same idea. So it's minus 9 plus 12 minus 5. So negative. Okay, so my absolute max is equal to, and just so we know, that's at x equals 2. And then the absolute minimum is going to be negative 5 at x equals 0. When it asks for just the extreme values, like I said, just don't worry about the local maximums and minimums for this one. Matthew? Yeah.
Would this be in the calculator section?
This would not necessarily be in the calculator section. There's other ways to check that I can show you. You could, because it's just a parabola.
How do we know that it's the absolute max if we're only checking within that?
We're given the domain of the specific function.
You're given the domain, so here, I'll graph it real fast. So we have what, negative x squared plus 4x minus 5? So when we look at this particular graph, we have to imagine that since the domain wasn't all reals. The domain was from 0 to 3. So 0 to 3. So I'm just looking at that part.
So the absolute maximum and minimum still have to be over the whole.
Yeah, so this would be a minimum here, right? This would be a max here, and
So
this
what-
would also be a min. But this one here is the absolute, and this one's the absolute max.
But if you didn't
This is
define,
just a local minimum.
if you didn't define a domain, there would be no absolute, there would be no minimum. Like, it's a problem.
Oh yeah, if it was all reals, there would be no minimum. Yeah.
But only because it's negative. Flip it.
Great. Okay, let's try another one.
I got to a point there.
Oh, you got to a point? Okay, so the first thing we want to do is do the derivative.
That was all.
So 2/3 x to the negative.
So we have to know how to do that.
That happened to me. Instead.
What? That's what you take.
In this case, I don't know if I left a pencil in here on Wednesday, whether it would be affected. Seriously. Seriously.
You can go buy another one first.
Is this your card?
Can you describe it?
A red mechanical pencil. That's like red. Yeah, exactly.
But doesn't equal zero.
No.
And say those things. Oh, darn it. I was beating you with gold. I said say those
I wasn't
things.
throwing it at you, I was throwing it to you.
Okay.
Still missed.
All right, guys, so let's look at the critical points here. Critical points. So if I try to set that equal to 0, it doesn't make sense. Okay, it can't be equal to 0. So we look, well,
Can't solve it.
yeah, there you would get 0 equals 2. Okay, so then we look at where f prime is undefined. I'm writing this out. You guys take notes where you need. So now we're looking at, when is 3x to the 1/3 equal to 0? Well, this implies x is equal to 0. Okay.
Why is that impossible?
Well, the only thing that you could have x, if you want me to, you can make it, let's say it's 3 cube root of x equals 0, so divide by 3, cube root of x equals 0, cube both sides, x equals 0. Okay, that's the long way. Hopefully, I would like you to recognize if you have a function that's just something x to any power and it's equal to 0, the only option is for x to be equal to 0. Now, one of the things that we brought up earlier is you need to make sure that the critical point is in the domain. So make sure it doesn't make the original function undefined. Sometimes that happens. And is 0 in between -2 and 3?
It is.
Okay, so we're going to check. Now we're going to check our critical points and endpoints. So we want to see f of 0, f of -2, and f of 3. Now, this may be a non-calculator type problem. So you just need to be able to recognize if you have x to the 2/3, remember that's the cube root of x squared. So you don't necessarily have to know what the decimal approximation is, but you should be able to compare them to see which one is the biggest versus the smallest.
Yeah.
So, okay, f of 0 is 0.
Got that one.
Okay, next one. Cube root of -2 squared. So that's going to be the cube root of 4. Right? And then the cube root of 3 squared. So that's going to be the cube root of 9. Which one is bigger? Cube root of 9. Okay, so the absolute
Wait, oh.
The absolute maximum is the cube root of 9, and that's when x is equal to 3. The absolute min is equal to 0, and that's when x equals 0. Just so you know, our first quiz, I actually have it set up so it says like absolute max. So you have a spot
Oh,
for that,
wow.
and then it says that x equals. So you just have to fill in the x value and the max. You don't need to remember to write it out this
I'm not for
way.
the test. See?
Yeah, I just have it written out this way, so it's easier to just put in the values.
Where there is no maximum,
There are cases.
but on the test, the quiz.
Oh, okay. Let me just remind you. I'm sorry to go back to this point. Do you remember how I said this extreme value theorem you need to remember? And I said, I probably should have gone back and reviewed this before we did the examples. If it's on a closed interval, it has to have both a maximum and a minimum every single time. Okay? Those are the examples we're doing right now. So if you have a closed interval, you have to have both a maximum and a minimum.
Oh, yeah.
Now, the maximum and the minimum could possibly be the same answer, but they still have to. One is a max, one's a min. Or they could,
Other than the same.
that would be like a constant function.
So what is it when you're a constant function and when you do it
Right, but you still just have one maximum value. It's still just one y value. Where it occurs, you could have, so just like the sine function, I talked about that first, like you think about the sine function. That has infinitely many places where it has a maximum, but it only has one maximum value. What's the y value where sine? Just one. And it has only one You understand what I'm saying? Like, there's only one y value that qualifies, but it could occur at infinitely many places. Okay, good questions. Did anybody do this one? No? There we go.
Derivative and negative stuff.
F prime, what's f prime? Negative e to the negative x, good. Okay, so. Let's see here. I can rewrite this as negative 1 over e to the x, if that helps. Is there any place where f prime is equal to 0? So is f prime equal to 0? No. Is f prime of x undefined anywhere?
No.
No.
There's no critical point.
No critical points.
You pick for you.
What if you do the x is no it's done?
Remember, an exponential function will never be 0.
But either 0
There's
or
nothing-
1.
Oh, okay.
There's no value that I could plug in that would make that a 0 there. So if there's no critical points, we only have to test
The endpoint.
the endpoints.
So even there's no critical point, you still have to test on.
Yeah, because one might be the
Yeah,
max, one might be the min. So we have to do f of negative 1. So that would be e to the first. And f of 1 would be e to the negative 1, or 1 over e. So your absolute max, just e, and that's at x equals negative 1. And your absolute min, 1 over e, and that's at x equals 1. Emma?
I have a random question. Not related to stuff. Do you guys ever figure it out that like x to the 2/3 is the same as cube root of x squared? Like who figured that that was your equation? Like how?
I don't think it was a matter of who figured out. It's a way that they learned to just define it one way. Like they use, it's all in the notation. The square root of x is the same thing as a 1/2. Which one came first, or did they, like in terms of notation? Yeah. Did somebody think about square root first, or did they think about rational exponents? I would think.
Say that.
It's always picked up.
I don't know. I don't know the answer to that.
I was thinking about it and I was like, oh yeah, how that happened?
Leibniz, always picked.
Leibniz is not French.
Sure.
German. Moving on.
French is German.
Oh, what about Newton?
Huh? What about Greek?
We're moving on. It's not always French. Okay, moving along. Extreme values.
See, you got me. Greek.
Yeah, this is it.
Okay, domain.
We talked about this. Oh, we don't say he's coming on the question.
Okay. So we don't have endpoints to check this time. Okay. All right, so just go ahead and find the derivative there. We're confused?
Oh wait. Oh. Well, no, because I'm confused with the critical points. If you feel like one critical point, you can't test any endpoint, and you have to have a minimum and maximum. Oh, because when you divide by 3, the 3 is a 0 critical point. Oh, they got rid of it. You can't do that.
Okay, so when we do the derivative, yeah, the 3 is not going to have an effect on where we have these critical points. You just factor it out. You can divide both sides by 3. Factor the right side, we get x minus 1 squared. So we just get one critical point. 1.
So we don't have to just use that.
Okay, so this is a cubic, right? This is
That
x
means
to
there
the
should
third.
be a minimum and a max.
It could possibly be. Or in the case of like just an x to the third, there's no maximums or minimums.
Alright.
So if we plug in 1, just plug in 1, we get what, 1 minus 3, and we get Now, some of you may, with an x to the third, is it possible to just have one maximum or minimum value? Okay, there's a way. I'm going to show you something that technically doesn't come until later, but it's really easy. I'm going to have you draw a number line for f prime. Leave some space here. Just leave a little bit of space.
How much space? Like for 2 lines?
I'm going to put a little plus and then like plus minus, like test values, and then I'm going to draw little arrows. Just to okay. Okay, I'm going to put -1 here. Now, because I labeled this f prime, the test values, I'm not going to plug in here. I'm going to plug them into my derivative. So just pick a number smaller than -1. Smaller than -1? Okay.
Yay, everybody.
Okay, we'll plug in 0 on the right. It's okay. So if I plug in -2, I like this one right here. This one right here is probably easier. If I plug in -2 minus 1 is -3 squared. So I get positive. And if I plug in 0, obviously I'm still going to get positives. Okay, so that means the derivative is always positive. That means the graph is going up and it continues to go up. So that means that the graph never went up and then came back down. So it couldn't be a maximum. And remember, if it had a minimum, it would be going down and then it would have to come back up. Remember when I labeled that big picture and I said it's got to go up and then come back down to have a maximum, and it's got to go down and then come back up? So it has no max and no min.
If it had been a positive and then a negative,
I don't understand how that.
like let's say 0 was the down arrow with a negative.
How can that not be a minimum? It goes down from -2 to -1.
No, no, no. Okay, these are just test values. These are not endpoints. I have no endpoints. The graph is basically, if I had to sketch this, you could graph it on your calculator to confirm. No. Let's double check. I mean, we could double check, but I can. So it's x to the third. Oops. I always forget to press the over arrow. And then I end up typing like the whole thing, and then I'm like, oh.
Yeah.
It goes up after that. You know that can't be a maximum. You're finding a local maximum. That's not like.
Okay.
So I don't add it to it.
So right here is the critical point. Right here was the critical point we were referring to, but it doesn't like switch to. You see how it doesn't have a maximum or a minimum? Okay, so
It's always increasing.
there's a reason that we find the critical points, and you'll see when we get further into this chapter. Part of it has to do with the concavity. Also, I know there's like more to it. Again, what happens in calculus is like if you pieces, it's too much to like put together all at once. But the critical point is valuable. The critical point is still important, whether it ends up being a max or min.
Okay, but what would happen if it was like arrow up and then the second part was
Down,
Yeah.
then it would be a maximum.
Then which one would be the maximum? The positive part?
The critical point would be where the maximum. This x equals -1 ends up being.
So let's say 0 was the negative.
Oh, so if it was going down,
Yeah.
then there would be a maximum.
At -1?
Yeah. Oh,
Wait, what?
Yeah.
Like, will that ever happen where it's going to be 1 arrow up?
oh, you know what? I made a mistake here.
Oh.
This was supposed to be 1,
What do you? What?
not -1. I'm sorry. I wanted to check my critical point.
Yeah, but the
It's okay. It doesn't matter because no matter what we plug in here, it's always going to stay positive.
So 0 was smaller.
Yeah.
Aha.
Okay.
It had to have been.
Let's try another.
Wait, like, for example, if it
Okay, so guys, when we do these, like if we went up and then it came back down, the critical point would tell us that this would be a max.
And if it went down.
And then if it went down and then went back up, there would be a minimum
At the critical.
at the critical point.
So there'd be, your critical point would be both max and or you could have two critical points. So you have to have two critical points.
Right.
But what if you had one critical point and it went down and up?
Then it would just be a minimum. Okay, go ahead and find the derivative here.
You're just using the calculator wrong. It wasn't, the only reason it's gonna have
We just have 2 more examples. We gotta try to get through these. Okay, so I wanted to show you the number line, just because the number line, you're asking about using a graph. Is that an easy way to check? Making the number line is usually easier if you don't have a calculator. I don't care if you use quotient rule or the power rule, chain rule. We could use that. That's what I would do. I would do -1/2. 4 minus x squared to the -3/2, and then don't forget, multiply by the derivative of the inside. So multiply by -2x. Remember how in the last chapter test I told you that it's important to learn how to simplify? It helps when you're trying to find critical points. That's why you don't want to leave negative exponents. So the -1/2 and the -2 cancel, but I'm left with an x. And then we are left with a 4 minus x squared to the 3/2 power. So we have critical points. Where would be the critical points here?
Why is there a negative? Oh, because it's giving that.
Okay, so let's set it equal to 0. So when we set it equal to 0, that's just setting the numerator equal to 0. And then if we look at where is this undefined, that's for any rational function. If you're looking for,
Okay, you're right.
so basically when you have a rational function, okay, and you're doing the critical points, for this part, set the numerator equal to 0. For this part, set the denominator equal to 0. You want me to write that down? Okay. Did we have a domain here? Oh, you know what? We didn't talk about domain. What would be the domain? Well, remember in the last one I didn't give you the domain?
You just set the denominator.
What's the domain in this case?
You have to investigate.
4 minus x squared has to be greater than 0.
Good. 4 minus x squared has to be greater than 0. So,
Squared is less than 4.
careful. What's the domain? What values can I plug in? They have to be between,
Try 0.
try 0. 0 works.
Yeah, because on 2 squared, 15 is good, on the outside is not good.
Right. So my domain is, now look at your critical points that we ended up with. No, because it's in the denominator.
-2 and positive 0. So we don't have to use them twice.
Right, yeah. I mean,
So actually,
I
what we
meant,
would do is add them 0 off and then we can multiply.
Well, but wait, look at,
Wait, is that including those points? Not including
remember how I
those
said critical points?
points? Wait, no,
Oh,
but
wait, they have
is
to
that
be
brackets or
15.
not brackets? This case of brackets or
So-
parentheses?
Parentheses.
Why
So-
parentheses?
Because it's in the denominator, it can't be 0.
You got it.
So these are the critical points that we came up with, but one of the important parts is that I that came up was that we have to make sure that the critical point is in the domain. Is 0 in the domain? Okay, so this is a critical point. But what about plus or minus 2?
No.
Right, so not critical point. Because not in domain.
It's just f of 0, that doesn't.
Right. I'm running out of room.
Or
I gotta
we
use a
could also
different.
use the endpoints.
This does not have
Just zoom
endpoints.
in and write smaller.
That. Oh, because then I'll back.
So now we're gonna do.
You should choose one that has space, so you can zoom in.
It's fine.
Oh, I didn't
So we're gonna check f of 0. What's f of 0? 1/2. So is this a maximum or a minimum, or is it nothing? Okay, so here's f prime. I want to check 0. 0 is my critical point. So here, if I plug in 0, or I'm sorry, if I plug in -1, what do we get?
Well, minus 1 is 3
So let's say I test -1, and then I test 1. If I plug in -1 to the derivative, do I get a positive or a negative? To the derivative. That's why I labeled this f
You're getting
prime.
positive.
You get a positive.
Okay.
You're getting positive.
Are you sure about a positive for
No.
-1?
Oh wait, no, negative x.
Here.
Top is
Guys,
negative.
This is going to be positive no matter what, right?
Look at the freaking top. It's
So if you get a -1 over positive, you get
I know,
minus.
You're what?
And then plug in 1, we get positive over positive.
You're a math. I don't know math. Like, yeah, I don't know math.
Okay. Yeah, you'll see I draw these arrows often. This is something, it's not, when it goes down, so the arrows actually kind of show what's happening with the actual graph. It's saying that the graph goes down and then it goes up.
So it's
So that means it's a minimum.
at x equals 0, so the minimum's at 1/2.
Right, so our minimum is equal to 1/2 at x equals 0.
One thing I think there would be negative.
How could it?
Because we get 1 over root 4, that's
Yeah, and
1
square root of 4
over
is
plus
just
or
2.
minus 2.
No, we're not solving x squared equals 4, it's just square root of 4.
Oh, yes. If you had it said x squared, you have to multiply it back. So you just have root 4.
If it just says root 4, then it's just positive. But if it says x squared equals 4 and you're solving, then you get plus or minus 2.
Is that convention or is that mathematically?
That's mathematically, that's always the case.
But the negative 2 squared is 4.
Yes.
So why is the square root of 4 be negative? Just take square root of 4.
No, because it's, the square root is positive. We're not saying, oh, is it negative or positive? We're saying it is positive and the square root of a positive is positive.
Why does it have to be positive?
Because that's the way it's written. Okay, we didn't get to the last one. We're out of time. Okay, but you have enough. This is just the last example. Would it help if I just continued with, well, maybe I'll pause it. I'll do a new screencast with just this last example.
Yeah.
Okay.
That sounds so great.